intermolecular forces, like how molecules interact with each other. So the first part of this that they do is they just do gas laws first. So remember that gases are really different from solids and liquids. When we talk about solids and liquids, you like mix salt into water. But it takes a whole lot more to mix gases into water. So that requires like some force. So things to remember about what they called kinetic molecular theory. This is really just like characteristics of gases. That one, gases are really far apart. So in this air in this room, gas molecules are very far apart and they're constantly moving. So they're like move. And their speed really depends on their temperature. So when you warm gases up, they move faster. When you cool them down, they'll move a little bit slower. But they're not attracted to each other. So they're almost like little independent particles. So there's no attraction between two gas molecules. They just are very randomly floating around. And their temperature, the temperature is directly related to the amount of energy that they had. So that's one that I just said. So if you heat it up, you're going to have faster moving molecules. You cool it down, it's going to move slower. So if I increase temperature, I'll increase their energy and actually their motion. And then vice versa happens, which sort of makes sense. So you can kind of think about if you heat, you can heat gases just like you can heat liquids, just like you can heat solids. Okay, so those are sort of characteristics that gases have. So in looking or doing measurements on gases and changes that undergo, there's three basic things that you talk about. You talk about their temperature. You talk about the amount of space they take up, their volume, and you talk about pressure. So we don't really talk about pressure with liquids and solids because pressure is based on the amount of force that a gas exerts against the walls of its container. So if you have a container and it has these gas molecules in it, those gas molecules are in constant motion and they bounce against the wall. Right? So they'll like hit the wall, bounce off, hit the wall, bounce off. And so that, how much they're hitting those walls, that's pressure. Okay, so it is the force on the walls of a container. Units, the units that they use for pressure, units are atmospheres, ATM. That's one we use a lot. Then there's millimeters of mercury, mmHg. So millimeters of mercury or inches of mercury, if you're talking about it in the old standard English units, that's really what they talk about in weather systems. You know how they talk about high pressure and low pressure? High pressure, they'll give those measurements in inches of mercury. When you've seen mmHg, you hopefully have seen that when thinking about blood pressure. So if somebody has a blood pressure of 120/80, that actually means 120 millimeters of pressure. So it's a measure of the amount of pressure on the walls of the blood vessels. So that's actually a liquid. But because the vessel has the ability to expand, you can measure the pressure on it. So both of these are millimeters of mercury. Right? And if you're 120/80, that's like perfect. Right? That's like the perfect blood pressure. Nobody has that. Okay? Instead, you have these patients that come in and they're like 200/110 and you're like, you're going to have a stroke. Okay? Too much pressure. So that's a measure of the amount of force on the walls of the blood vessels when you're talking about blood pressure. PSI, this is like if you have to put air in a tire. That's PSI, pounds per square inch. So that's like how much force would be on the inside of that tire. That's how that number gauge comes. But we don't really use that in chemistry very much. Really, you're going to see atmospheres in millimeters of mercury. Way more than you'll see any of these other ones. Okay, so just as a note, atmospheres and mmHg, those are the most common ones that you'll see in chemistry. So they originally used to measure pressure of gases by monitoring how it affected the column of a sample of mercury in a tube. So that's where that name mmHg originally came about. So I think you're pretty much all too young. All too young to remember this, But in the doctor's office, there used to be this on the wall. So there used to be a very tall column, and that was where the mercury was in the little pool in the bottom. They would hook the blood pressure cuff to you, and it was like on this really long accordion, hook it to you, and they would pump it up, and you could actually see that silver mercury going up the tube, and then as they would release the pressure, it would drop back down. So that mercury was a 1 centimeter diameter tube that it would go up and down in. When measuring what they call atmospheric pressure, so your atmosphere, the air that is above, pushes down on this little pool of mercury, and that actually pushes the mercury level higher or lower depending on the pressure. So have you ever heard in weather, when they say it's high pressure, there's a high pressure. So they have, like on the weather map, they'll have the H. There's an H coming across. High pressure is associated with sunny, dry air, which means that there's less moisture in it. High pressures are always like nice weather. Low pressures, and they're like, and then comes in this low, where the high and the low are coming together. Low pressure areas, in terms of weather, are like what's coming through tonight. There's a low pressure system coming through, and so what's it doing outside? Yeah, it's about to rain. And so low pressure areas are typically associated with like rain, moisture. So humidity really has to do with the amount of water vapor that begins to collect. And it has to do sort of like with the amount of water that's present in the environment anyways. So areas like close to the equator, humidity is always higher. As you go further north or further south from the equator, then you tend to have drier air. You have less humidity as a whole. But so that's not so much, that's more like related to climate and the amount of moisture that's already at the surface of in that region. So like when you think of the desert, there's not a lot of water, and so it's not very humid. Like out in Arizona, super dry. California, well, right now it's not, but you know, normally California is really dry. Right now they're having like mudslides and floods and all kinds of craziness. But normally it's because there's not a lot of vegetation compared to here. You know, so we've got all this green, so we've got a lot of lakes, a lot of moisture, and that adds to the humidity. So really high pressure systems and low pressure systems are those that are variable. So high pressure brings along sunny, dry kind of air, whereas low pressure is going to bring in rain and kind of moist air. Low pressure because there's more water vapor and less actual air. So in taking pressure and going into the first, what's called a gas law. So Robert Boyle, and so remember when I told you that like radiation and radiation chemistry was like, it evolved sort of in the very late 1800s, right around 1900? This is way back in the 1600s. So this is much older. Understanding of gases and how gases behave is much older in terms of the history compared to some of the other stuff we've talked about. So this was like 1600s. Robert Boyle was looking at how pressure and volume were affected. So he took a sample of gas, he kept the temperature the same. So that means those molecules were vibrating and moving at the same amount. He found that if he started with this, and so we'll say each of these little increments is a volume. So do you see that this is like 3 volumes? Okay. So if the little syringe is all the way up at the very top, and we'll say that this is the initial pressure. If he took and pressed down, put twice the amount of pressure on the little syringe from the top, if he doubled the pressure, what happened to the volume? It went from 3 to like 1.5. So you see that? So if I doubled the amount of pressure I'm pushing on the little syringe, then the volume would decrease to about 1.5. If I went and I put 3 times the amount of pressure, so I pressed 3 times harder on the syringe, what would the volume end up being? Just 1. Do you see that those are there's a relationship between them? So like 1 times 3 is 3, 2 times 1.5 is 3. 3 times 1 is 3. So their relationship, they're said to be proportional. They're indirectly proportional. If I increase the pressure, I always decrease the volume. If I increase the volume, then that's going to decrease the pressure. So if one goes up, the other goes down. So in this one, I doubled the pressure and that halved the volume. If I triple the pressure, it made the volume a third. So one goes up, the other one goes down. The application to this is breathing. So breathing, like actual ventilation, pulling air into the lungs, your lungs don't do anything except stretch. Your lungs are really not involved. But breathing is a change where the increase in volume decreases the pressure and vice versa. And that's the reason that air gets pulled in or out, pushed out of the lungs. So here's sort of the example. So this first one, so along the top, this is if you're in an inhale. So kind of think in your head, if you sit there and you like exhale to a normal, and then you go, so you start your inhale. So the reason that when you inhale, you hear air flowing in is because inhalation, this is an active process. It is an active process because it uses muscles. Muscles contract, 2 groups of muscles. One set of muscles is called the external intercostals. The external intercostals are the muscles between your ribs. So you know that you got 12 pairs of ribs going down both sides. There's muscles in between. So if you kind of feel for your ribs, in between each, there's muscles that connect those ribs. They're the external intercostals. When they contract, they pull your ribs up and out. And you can kind of feel, if you take a deep breath, you can feel your ribs come up and out. The other muscle that kicks in is your diaphragm. Your diaphragm is the muscle that splits your thoracic and your abdominal pelvic cavities. When the diaphragm, it's normally like this. When it contracts, it goes like this, right? So it gets smaller, it gets shorter. Remember when muscles contract, they shorten. So when your diaphragm's relaxed, it's like domed. And then as it contracts, do you see that that's shorter? So as it contracts, it actually goes down. So notice then your ribs go up and out. Your diaphragm goes down. So what is that going to do to the volume? So that's before you take your inhale. This is when you start. What happens to the volume? Does it go up or down? If this goes up and this goes down inside of the thoracic cavity, the volume goes up. Okay? So this increases your volume inside the thoracic cavity, inside of your chest. So what does that do to the pressure? Lowers it, right? Because remember, one goes up, the other goes down. So that decreases the pressure. Negative pressure is suction. So now this creates suction inside of your airway. And to relieve that suction, you allow air to flow in. So this pulls your air in. Increase in volume, decrease in pressure, which then acts to suck air into the lungs. So remember, you got your trachea, the bronchi, the little airway branches. And so the lungs are really kind of just this elastic, stretchy tissue. So these pull air in, the lungs inflate, increasing in their volume, and that helps to bring the pressure back to normal. So you can kind of feel that when you go, it reaches a point where it just sort of like levels off and you stop inhaling. That's when the pressure balances. So increased volume decreases pressure, which creates suction to help bring air in and balance the pressure back out. So now you're at an inhale. You're at the very top of the inhale. To do an exhale, it's the exact opposite. To do an exhale, exhale is passive. Passive because muscles relax. Your muscles don't have to contract when you exhale. In fact, if you watch somebody sleep, right, they go, right? That exhale is like this kind of slow, steady. It is actually because those same muscles that created the volume change, they relax. So if muscles relax, then the ribs go in and down. When the diaphragm relaxes, the diaphragm stretches and goes back up. So it bends up, going back into its dome arrangement. What does that do to the volume inside? It's going to decrease the volume. So now my volume's going back down. So what's that going to do to the pressure inside? That's going to increase the pressure. See how they're opposite. Positive pressure is the push. That's what actually blows air out. So that increase in pressure pushes air out of the lungs. So the lungs are really just there. The lungs are just this they're like balloons, little spongy, elastic balloons. The lungs have no ability to inflate themselves. The lungs don't swell up automatically. They're really just responding to changes in pressure and volume. So then we get back to the original, where that air flows out versus air flowing in. So that's a pressure and volume example. If one goes up, the other goes down. Now we can do this in math. We can actually calculate pressure and volume. So remember I said if we're talking about pressure, values you're going to see for pressure. So pressure is either going to be ATM, which is atmospheres, or it might be mmHg, which is millimeters of mercury. Now, volume is always going to be liters. Okay, so those are the units to help you identify if you see ATM or if you see mmHg, you know that's pressure. If you see liters, then you know that that's going to be volume. So in this one, you will always have 3 out of 4 numbers. You've just got to make sure you know which one's which. So they have found, Boyle found, if you have a gas at initial pressure and volume, and you change one of them, the other one will change to create this inverse proportion. Sometimes, and I'm one that I think of it as P1 V1, because that's like the initial. It's going to be equal to P2 V2, which is the final. So initial, final, 1 and 2, you can use either one, whichever is easier. So you will know 3 of the 4 values. So then it's just a matter of solving for the one that you don't know. So here's kind of like the steps. So for me, always determine what do you know. Like, do I know P1, V1, P2, V2? Which 3 do I know? Identify those, and then identify which one don't I know. Then I got to solve the formula for the missing one, the one I don't know. And then you can just plug the numbers in. I find it's easier to rearrange the formula, then use the numbers, than to try and move the numbers around. Just tend to make more mistakes that way. And remember to use significant figures and rounding, because this is multiplication, so significant figures and rounding come in. So here's one. So how are you going to need a calculator? Okay, so if a sample of gas changes from a volume of 82.3 liters to 26.5 liters, what was the initial pressure if the final pressure is 1,825 millimeters of mercury? Okay, so look at your numbers. So remember we've got P1 and V1, P2 and V2. So going across, first number, 82.3 liters, what is that? So is it V1 or V2? So if a sample of gas changes from 82.3, so that is V1, and it goes to 26.5, so that is V2. What was the initial pressure? So usually you'll see in like the second sentence or the second half, when you see the what was kind of thing, that's going to tell you, so initial pressure, I need to find P1. Right? I don't know what that one is. What was the initial pressure? But the final pressure is 1,825 mmHg, so that is P2. Okay? So read through the question, underline any numbers. Remember, if there's millimeters of mercury or ATM, then you know it's pressure. If it's liters, then you know it's volume. So identify them. You can identify them by just underlining them in the problem, or you can like write them out, okay? Whichever one's easier. So next, P1 times V1 equals P2 times V2. So what do I have to get all by itself? P1, the one you don't know, I've got to get all by itself. So if I look at this formula, V1 is over with P1, so I have to move V1. How do you move that? That's a 1. See how P1 and V1 are both on the same side? I want P1 all by itself. So what do I have to do to both sides? Divide what? So if I divide by V1, do you see what it does to V1 on the left? What do they do? Yeah, do you see that those will cancel? Okay, so you just look, you've got the 4, whichever one you don't know, you've got to get it by itself. So typically it means you're going to have to move one of the units to the other side. So now I have my formula. P1 is P2 times V2 divided by V1. Then just plug it in. So I know that P2 is 1,825 mmHg times V2, which I know is 26.5 L, and then V1 is 82.3 L. Always go back and just double check, because I have people that like flip their V, they know V1 and V2 and they put them in the wrong place. So just double check that you put them in the right order. Then just put it in the calculator. So I'm going to take 1,825 times 26.5, 1,825 times 26.5, and then I'm going to divide it by 82.3. Liters and liters will cancel. My answer's in mmHg, pressure. I got 587.636695 mmHg. Put it in your calculator and tell me if that's what you got. Is that what everybody got? Anybody not get that? Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8. There's 9 significant figures in that answer. So I know I can't keep all of those. So the last question, so I do the math. And then apply significant figures. Since this is all multiplication and division, I know I have to go by significant figures. So looking back up, 82.3, how many significant figures? So see that there's 3 significant figures, 1,825, 4, and then 26.5, 3. So I know that I have to have just 3. Remember, the smallest number of significant figures in the problem. So when you start with your answer, start from the left, underline the first 3 significant figures you come to. So the 5, the 8, the 7. The next number is a 6. So what's that going to do? It's going to round up. So this would be 588 mmHg. So just make sure that you apply the significant figures at the end. So just follow these basics, follow these steps. That way you're not going to miss those. Try another one. So when you go through and read this, okay, so when you get done, so reading through these, if the pressure of a sample of oxygen changes from 2.5 atmospheres, that's P1, because it changes from this, so that's the initial, 2.5 atmospheres to 6.4 atmospheres, so that's P2. What will the final volume be? That's your question mark. So V2 is the question mark if the initial volume was 0.025 liters, so that's V1. So I just listed them out. So see if you got all of those. Then the next step is to just put P1 V1 equals P2 V2. I want to get V2. I have to divide both sides by P2. That's going to move P2 over to the other side. And there's my final formula. So that way now I have the one unknown I've got. All the knowns are over on the other side, so I can just plug them in. P1 is 2.5 atmospheres. V1 is 0.025 liters divided by P2, which is 6.4 atmospheres. And this is the number I got. So 0.009765625 liters. Did anybody not get that? Okay. Now you have the last step. You've done the math. Now you just have to round. So how many significant figures should my answer have? 2. 2.5, 2 significant figures. 0.025, 2 significant figures. 6.4, 2 significant figures. Right? Remember, zeros out front are not significant. So I'm going to keep these zeros, but the 9 and the 7 are the first 2 significant figures I get to in my answer. And the next is a 6, so what will that do? That'll round it up. So it will be 0.0098 liters. So I use the least number of significant figures in my problem, and in this one, all my problems are all 2 significant figures, so we just have 2. Okay, so they say that Boyle's law is inversely proportional. So you remember that you should see if one goes up, the other goes down. And so we can set them up so they're equal. P1 times V1 equals P2 times V2. There's one other we're going to talk about, and that's Charles's law. So Charles's law, he didn't look at pressure, he looked at temperature and how it affects the volume of a gas. So this one, you can kind of think of like a hot air balloon. So if they begin to turn on a fire and heat the gas that's in a balloon, what happens to it? Right? So you have an increase in volume, right? So if there's some amount of gas inside of the balloon and you begin to heat it, then you begin to see that it swells. And then eventually, like it'll rise, so it's lighter than regular air, so it goes up. And that's how they can adjust by keeping that balloon expanded. He found, unlike pressure and volume, he found if you increase the temperature, that'll increase the volume. So my example with this is, so I have a child, both of my kids are in their 30s, but during their early years, like through elementary, middle, and even into high school, because they enjoyed it. So they were like, aren't you going to do this again? So I got a lot of pressure to continue it. But, so they used to get a balloon, one balloon for every year of their birth. Okay, so all of them would be just regular latex balloons and then one fancy Mylar balloon. So where do you go if you have to buy 12 balloons? Dollar Tree, right? Okay, so like you're not going to go to Harris Teeter because they're like going to cost you $4 a piece. So you can go to the Dollar Tree and get them. Now they're $1.25, but they used to be $1. Okay, so yeah, my kid was 15. Sure, I have only $15 worth of balloons. Problem is one of them had birthday in June. Hers is the middle of June. It's not that hot. But the other one, bless her heart, was born the end of August. So the end of August in North Carolina. And so it just doesn't even matter. It is always still like blazing hot. So drive to the Dollar Tree, get out of my car, go into the store, and I'm like, I need 15 balloons, 14 balloons, and one of these Mylar balloons. And so the girl's like, all right, so she starts filling them up. So in the meantime, my car is sitting in the parking lot, which is asphalt. And by the time I get back to my car, it's like 100 degrees in my car. So now I'm taking these balloons that are coming out of a 70-degree building where they've just been blown up, and I'm going into this 100-degree car. So what happens to the gas inside of the balloons? Temperature goes what? Up. And if temperature goes up, what happens to volume? And inevitably, I will be driving home, and I will lose at least one or two of them. So you're like driving home, pow! You're like, ah! And that's because that gas begins to warm, the balloons expand, and they expand because, she just blew them up. So they're already tight. They don't have much expansion that they can go through. So I'd get home, and they'd be like, why don't I have, like every time. So I would just be like, maybe I should just buy an extra because I know I'm going to end up losing one. So that went on until they were like 17. And even now, she was like, remember when you used to get us balloons? So it clearly made a impression on their little lives. But same thing happens. Temperature goes up, volume goes up. So by the flip of the coin, if you have a sample of gas and you keep the pressure the same, because this is one where you have to keep the pressure the same, if the volume goes down, the temperature will go down. So if you take a sample of gas and decrease the volume, that will decrease the pressure as well. So these ones, see, they're not opposite, they're the same. So they say that these are that these are directly proportional. So if one goes up, the other goes up. One goes down, the other goes down. That's if you keep the pressure the same. So Dr. Charles was the one that studied all of this. And again, he was in the late 1600s. So he was pretty close in time with Boyle. But he had a problem. And the problem he had is if he studied gases, everything worked great in his calculations and his experiments, unless he was using gases that were below 0 degrees Celsius. If temperatures went below 0, then they'd be like -1, -2, -3 Celsius. Then his numbers didn't work. So he said, we can't have a scale of less than 0. And that is where absolute 0, or the scale of Kelvin, came into play. So with gases, Kelvin, this is a scale of temperature that is used for gases. It has the exact same scale as Celsius. So this is nice. So the each increment, 1 degree Kelvin, is the same as 1 degree Celsius. So if you increase 10 degrees Celsius, that's the same as increasing 10 degrees Kelvin. But the 0 point is what they call absolute 0. So absolute 0 is 0 degrees Kelvin. Absolute 0 is described or defined as the coldest possible temperature that you can have molecules at. That is the temperature. Remember we said temperature is like a measure of the vibrational activity of molecules. The more molecules vibrate, the higher their temperature. So absolute 0 is when molecules stop vibrating. If they stop vibrating, they can't have a temperature any lower than that. That is absolutely as slow as they can be. And that is at negative 273 degrees Celsius. It's equal to minus 459 degrees Fahrenheit. That's how cold it is. Yeah. So everybody's like, I don't even understand Celsius. Well, minus 459 Fahrenheit. That's 0 degrees Kelvin. So it's really cold is basically the point at which molecules stop moving altogether. Coldest possible temperature. So we've got to put temperatures into Kelvin for any Charles's law calculations. It's pretty easy though, because I told you the scale's the same. So if you're given Celsius and you want to find Kelvin, all you do is add 273. If you find Celsius and you want to go, or if you have Kelvin, you want to go back to Celsius, you just subtract 273. It's the same, the scale, each increment is the same. It's just the difference in where the 0 is. 0 Celsius and negative 273 Celsius is 0 degrees Kelvin. But we're going to do the exact same thing, because if we have V1 over T1 equals V2 over T2, you will always know 3 of the 4. If you ever get a temperature of Celsius, you've got to put it in Kelvin. That's kind of like the only thing that's different than boils that you've got to make sure that you do, is any temperature values have to be put into Kelvin before you can use them. So here's this one. A sample of gas has a final volume of 24 liters at 105 degrees Celsius. What was the initial volume if the initial temperature was 25 degrees Celsius? So running through, so a sample of gas has a final volume of 24 liters. So what is 24 liters? That's V2, right? So remember, liters is volume. If you see liters, it's volume. If it's 24 liters at 105 degrees Celsius, what's 105? T2. What was the initial volume? So what do I want to find? So V1 is what I don't know. If the initial temperature was 25 degrees Celsius, so that is this is T1. So again, then you can go, if you want, you can go and make the list. I'd encourage you to do this because you have to do the temperature change. So V1, we don't know. But T1 is 25 degrees Celsius. V2 is 24 liters. T2 is 105 degrees Celsius. Okay, so I identify. Second thing to do, convert all temperature to Kelvin. Before you even go any further, all I have to do is to go to Kelvin, just add 273 plus 273. So this is 298 K. This is 378 K. 105 plus 273. So figure out which one, what your units are. Convert anything that's temperature to Kelvin. Now, what do I got to find? So what do I got to move? How do I move T1? See, it's in the denominator. What do I have to do to move it? Multiply both sides. So if I multiply T1 times T1, do you see that now T1 and T1 over on the left will cancel? And so now T1 is in the denominator in the top over on the right side. So V1 equals V2 times T1 divided by T2. So does everybody see that? And a rule of thumb, if what you need to move is in the denominator, it will always end up in the numerator on the other side. If what you have is in the numerator and you got to move it, it always ends up in the denominator. So when they switch sides, it's always going to go from on top to the bottom, from the bottom up to the top. So now I just plug them in. Just be careful that you do them. So 24 liters is my V2 times T1, which is 298 Kelvin, and then divided by T2, which is 378 Kelvin. Kelvin and Kelvin will cancel. So 24 times 298 divided by 378 comes out with a whole bunch of numbers. 18.92063492 liters. So put it in your calculator, make sure that you get that 2. Remember, you just multiply everything across the top, divide by each thing in the bottom. Now, when you do significant figures, because some people would say, well, look, T1 at 25 degrees, but 298. So when you do this, always go back to the numbers in the problem to figure out how many significant figures. In this one, it really doesn't make a difference, but it might in another one. So 24 liters, how many significant figures? 2. 105, how many significant figures? 3. And then 25 has, so I know my answer has to be rounded to 2. Oh, thank you. Okay, so starting from the left in my answer, the first 2 numbers, the 1 and the 8, those are my first 2 significant figures. The next number is a 9, so this will become a 19. Yep, see? 24 liters, 2 significant figures, 25 degrees Celsius, 2 significant figures. So don't go based on the numbers in the problem. Okay? When you're doing your rounding, go based on the numbers in the problem. Okay? Instead of taking the Kelvin numbers.
Being that it's only 2 for liters and not 3 for...
Right, so 24 has 2 significant figures. Well, but 25 degrees Celsius is only 2 significant figures as well. Okay, so there's still 2 significant figures is the smallest number, and that tells you, remember, you're always using the least number of significant figures in the problem. Okay, all right, so one more. So see if you can do this one. All right, so in this one, so kind of check yours, see how you did. So in reading it, 12.5 liters is V1. T1 is 15.5 degrees Celsius, and I have to add 273. V2, I don't know. But T2 is 89.5 degrees Celsius, and I have to add 273 to that. Okay? So first identify what are my units, what do I know, which one don't I know. Anything that's temperature, add the 273. Second thing, setting up the formula, V1 over T1 equals V2 over T2. Since I gotta find V2, that means I gotta move T1 to the other side. So if I multiply both sides by T2, that'll allow T2 to cancel on the right, moving it over to the left side. So here's where my formula ends up being. Then it's just a matter of making sure you plug in the right one. So double check. So T2 is 362.5 Kelvin. V1 is 12.5 liters divided by T1, which is 288 degrees 0.5 degrees Kelvin. And I got 15.70623,917 liters. Okay, did everybody get to that point?
So whenever it comes to the equation, you have to multiply on the side that you need to find.
So in this, so here's what the equation is V1 over T1 equals V2 over T2, right? So that's the equation. So when I know the reason you do the first part is figure out what I don't know. So I don't know V2. So that means that I need to get that all by itself. So I've got to move T2. Okay, so to move anything in the denominator, if you multiply both sides, then that way those will cancel and it'll move it to the other side. So I have to get this alone to be able to do the math. Okay, and so once I got it all by itself, I moved T2 over to the other side. V2 is now all by itself. So whether you're doing Boyle's or Charles's law, it's the same thing. You'll know 3 of the 4, and you've just got to kind of practice the rearranging of the groups in order to get them to work. So I've had other students say, well, couldn't you like cross multiply? So some would want to like cross multiply. Yeah, you could do that, but you'd still end up with the same formula. Okay, you'd still end up having to move T2, T1 would be moved out of the way. So either way, if you cross multiply or just rearranging the formula. The other little note to remember is if you need to move something in the nominator, it always goes to the denominator on the other side. So if it's in the top and I got to move it, it'll always go over to the denominator on the other side, like what we did with Boyle's with Boyle's law. So if I have P1 V1 equals P2 V2, everything's in the denominator, right? Because they're just all multiplied across. So if I have to move P2, it's going to end up in the denominator on the opposite side, because I'll have to go the other way, because I will have to P2 to get rid of it, to move it if I want to find V2. So notice how it goes to the bottom. So if you move units that are in the denominator, they'll always be in the denominator on the opposite side. If I have something in the denominator I need to move, it'll always go to the nominator on the opposite side. Just as sort of a like way to remember that. All right. So what about the last thing? So what about significant figures? How many significant figures should this answer have? 3. 12.5, 3 significant figures. 15.5, 3 significant figures. 89.5, 3 significant figures. So look at the numbers in the actual problem. Since 3 significant figures, that means that I keep the 1, 5.7. So everything else does what? Because this next number is a 0, so all that just drops off, right? So it'd be 15.7 liters. 3 significant figures in my answer. Okay, so Boyle's Law, Charles' Law. Those are the two. Now, there's actually a whole bunch of others. We have Gay-Lussac's Law, but we're not going to bother with it, okay? We have what's known as the, like, talking about, like, changes in state, but we're not going to really do a whole lot with that. So we're going to jump forward. So we're going to jump forward and we're going to talk about what about solids and liquids then? So if gases have this, like, no attraction, but solids and liquids do. Like, why does water cling together? Why does oil and water separate? So really this middle section of the chapter is all about like what they call intermolecular forces. Intermolecular means between molecules. It is the attractive force between two molecules. So if I have 2 water molecules, this interaction, their attraction or repulsion, that's an intermolecular force. So it's not like a bond. So it's not like ionic or covalent bonding. It's really like when you have 2 different molecules, why are they attracted or not? The higher their attractive forces, typically, the more stable they are, the higher their boiling points. So in fact, salts, they have the strongest intermolecular forces, which is why salts exist as crystals. You have to heat sodium chloride to about 1800 degrees before it'll melt. 1800 degrees Celsius before it will melt. Really high. You have to get really hot because it is super attracted and stays in that crystalline rigid shape, which is pretty cool, but you can throw it in water and it'll dissolve. But if you have like a crystal of sodium chloride, you have to really heat it to break the attraction between the sodium and the chloride ions. So we're going to run through, these are the 5. First one, London forces. These are the weakest of all forces. All molecules have London forces, but London forces are really pretty weak. These are the forces that you see with nonpolar molecules. So remember when we were talking about nonpolar molecules, like the fuels? Have you ever gotten gasoline on your fingers? So gasoline's like, it feels kind of slippery, but then it's gone, right? So it like evaporates really quickly. Has that kind of slippery feel, but it doesn't really stick to your fingers. It just kind of like feels like it like falls off. So I always said, I would think of nonpolar molecules as being like 2 pieces of plastic. They're just not that attracted to each other, right? So if you have 2 pieces of plastic side by side, they don't really, like, there's very, very little sticky. I like their example though, because they said that London forces, you can think about them as being almost like cling wrap. So have you ever pulled like saran wrap or cling wrap? You pull the plastic wrap out and you tear it. And inevitably, one corner folds over. So then you go and you try to pull this corner and then what happens? Another corner. So you're like, so pretty soon you're laying it down and you're like, okay, I got it. You go pick it up and go, Foop. That's really what a London force is. London forces are where you have this like instantaneous imbalance in electrons that are being shared. Because remember, these electrons are shared evenly. But every once in a while, more electrons might be ending up going over to one side of the molecule than the other, just in their regular bonding. And so that can create a slight attraction. But as soon as it's formed, it goes back. So they call it like a spontaneous slight charge that disappears as soon as it's formed. So if you look at like this first one, so if you look at this, do you see where these electrons are all evenly distributed? So remember that this bond is 2 electrons, 2 electrons, 2 electrons. Every bond is 2 electrons. If they are equally distributed between the carbons and the hydrogen, like going back and forth equally, then this is a really uniform looking molecule and is very neutral. But every once in a while, see how the red and the purple do? See, every once in a while, more electrons end up around the hydrogens at the top than around the hydrogens at the bottom. And because of that, you can get this slight charge. That's the whole reason that cling wrap will cling. Like, think of it like that. But as soon as it's formed, it disappears. So this is extremely weak. Like, doesn't take very much to break this. This doesn't create much attraction. In fact, molecules like CH4, they're a gas at room temperature because they're so not attracted to each other, they evaporate quickly. So these are a gas at room temperature because there is little to no attraction between those molecules. So if I have one CH4 molecule and another CH4 molecule and another CH4 molecule, they could care less about each other. They're just like floating away. So London forces are the only forces that would create any attraction at all. And that's only not in nonpolar molecules. This is the only kind of attraction they have. But polar molecules now have a slight positive and negative arrangement. So this one is showing an ether. So remember how those oxygens have those 2 pairs of non-bonding electrons? Remember up around that oxygen, remember nitrogen, oxygen, fluorine, and chlorine, those 4? If you have only one of those and it's a relatively small molecule, that creates a polar molecule. So in this is going to create this slight negative. So remember the slight is that funny looking little figure 8. You can kind of see it at the top where the red area is on each of those molecules. That means now down here, this side becomes slightly positive. So now you have a slight positive and a slight negative. Now they're going to start stacking. So do you see how they kind of start arranging themselves? So that where the slight positives are going to line up around the slight negatives of other molecules like them. They call that dipole-dipole. So remember that this is polar. Dipole-dipole are polar molecules, much stronger than London forces. And this kind of creates like a stacking. So these molecules want to hang out. These molecules want to start kind of clinging together because of this opposite charge attraction. So any molecule that has a nitrogen, oxygen, fluorine, or chlorine, it's going to have some of this. It's going to have some of this imbalance in terms of its bond sharing and this slight positive negativeness that you're going to see. So that's all you look for. The third one. The third one has a name that says bonding because this is a polar molecule that creates a much stronger attraction because of the ability to almost share hydrogens. So they call it hydrogen bonding. This happens if you have an oxygen or a nitrogen that has a hydrogen attached. So a good example of this is water. So remember that water kind of has that bent shape. Water is definitely polar. So this side becomes, around the oxygen becomes negative, around the hydrogens become positive. But when another water molecule comes along, this second water molecule is going to want to, the oxygen is going to want to like slide up close to the hydrogen of the other oxygen. And it creates this attraction. So they use this little dash, dash, dash to kind of like connect the two. This is even stronger than just being polar. It's stronger than just being slightly positive and negative. The electrons of the oxygen are attracted to the hydrogen of the other water molecule. Because remember that hydrogen, its electron really hangs out near the oxygen. So like that blue hydrogen is really almost just like a little proton, because its electron is around the blue oxygen. So when the purple oxygen comes along, it's like, oh, a positive hydrogen. So there's this attraction. This is even stronger. And the only time you're going to see this is you will see this. You're really not going to see it in life, like in living things with fluorine, because there's not a lot of fluorine in your body. But you're going to see this if there's a nitrogen or an oxygen and one of them has a hydrogen. So I can have something like this. Doesn't matter what everything else is. And then it can be a nitrogen over here. This can do hydrogen bonding. So the nitrogen with an oxygen, if I have an oxygen with a hydrogen and a nitrogen, hydrogen bonding can occur. The nitrogen could have the hydrogen, and the oxygen would then be attracted to it. So it's almost like that hydrogen ends up kind of being held between them. So if one oxygen or one nitrogen has a hydrogen, and then there's another nitrogen or oxygen around, that will create this hydrogen bonding. This happens in proteins. This happens in the nucleic acids. This is really like what helps to hold, like the double-stranded helix is held together by hydrogen bonding. So in living systems, this really does come into play. They say that a hydrogen bond is only 1/10 as strong as a covalent bond. So hydrogen bonds are 10% as strong as a covalent bond. But when you have hydrogen bonding, a lot of times there's a lot of them. So there'll be hundreds of hydrogen bonds. And that creates a much more attracted molecule. This attraction is the reason that water is a liquid at room temperature. Even though it's a very small molecule, it's just H2O, it's just one oxygen and two hydrogens. It is roughly the same size as CH4. Like if you looked at the mass of carbon and 4 hydrogens versus the mass of oxygen and 2 hydrogens, CH4, methane, is a gas at room temperature because it's nonpolar. Those gas molecules, they don't care about each other. Like they're not attracted because they only have London forces. But water has hydrogen bonding, and that's why water has such a high boiling point, because water molecules like to cling together. So that hydrogen bonding is what does it. So there's kind of like a picture. So you can kind of see, here's a water molecule, and then this other water molecule comes along and creates that dash, dash, dash. That connection, it's stronger than just being polar. And then here comes another one. So the little dashes are between. So in 5 water molecules, I have 4 hydrogen bonds right there. And then there's actually water molecules behind these, water molecules in front of these, above and below, because if you have like a cup of water, there's water all around each water molecule. So it creates this really strong attraction. This is really like the strongest attraction of normal bonds, of normal covalent bonds. So here, this shows how hydrogen bonding, so see this alcohol group here, the OH? So we can have hydrogen bonding of different groups on this one alcohol. So I have 4 molecules and 3 hydrogen bonds. So that really begins to take a bigger effect. And then sort of the topic. So water, it is your universal solvent. You are roughly 2/3 water, so about 62. You're more water when you're a baby. So you're about 68. They're all wet and dewy. So like their little cheeks and everything, they are very well hydrated. The older you get, you start to lose water. That's why we get stringy. Why we end up getting all thin-skinned and wrinkly. We lose that water. So you kind of you stay about in the 60% though. So lower as an older person, less as a baby. Water molecules have this hydrogen bonding. So they have this really strong attraction for other water molecules, and this is why they have a really high melting and boiling point compared to other molecules their size. The other thing is it takes a lot more energy to break the links, to break that attraction. So it's a higher melting and boiling point. In order to boil water, you've got to break the hydrogen bonds. That also means that you have to put a lot of heat into water before it changes temperature. So that is why they say water has a very high specific heat. Specific heat is how much energy something absorbs compared to its change in temperature. So you've got to put a lot more energy to get water to boil than you would to get ethanol to boil. Ethanol boils at about 80 degrees, but ethanol doesn't have the strong hydrogen bonding that water molecules have. That high specific heat is beneficial to us because this means that you can absorb and release a lot of heat energy, but your body temperature stays the same. Since we are made of so much water, our body temperature tends to stay the same, or it just changes slowly. So one thing you can think of is like a pool. So in a couple of months, people are going to open their outdoor pool. So if you open your pool, like say the end of April, what's the temperature of the pool in May? Pretty cold, okay? So it stays, so it doesn't just warm up overnight unless you have a heater. But if you don't have a heater and you wait for the sun and just the regular temperature to do it, the entire month of May, it's like in the 60s. So you put your toe in? No. So it's still cold. But even though we have 80, 85 degree days in May, that water is still going to feel cool until you start getting into July. Now we've had the days long enough that the water has absorbed energy and now it's gradually changed temperature. So then in August, good God, in August sometimes it's like 75 degrees. You get in and you're like, it's really kind of gooey. It's too warm almost. The water gets too warm. But then come in September, temperature starts to drop. But what's the temperature of your pool? It's still warm, right? So in September, the temperature will still be in the 70s, even though we have some nights that drop into the 50s. So it heats up slow and it cools down slow. So we're this way too. Even though you go out and you exercise or you go out and it's freezing cold outside, you don't change temperature that rapidly, and that's because you're so much water. So that high specific heat, it's really due to hydrogen bonding. Third one, stickiness. Water likes to form a raindrop, right? So all these water molecules, they're all attracted to one another and they form this droplet. All the water molecules being attracted, they all kind of pull in together. That's why water forms as a drop. So they say water has a cohesiveness. Water likes to cling to itself because of hydrogen bonding. This is a problem for babies that are born premature because one of the last systems to develop is what? Anybody had a preemie? They always have what kind of problems? They have problems breathing. That's always the biggest issue. So if you have a baby that's earlier than 35 weeks, the biggest challenge is they got to watch and see, are they struggling to breathe? Are they in respiratory distress? And that's one, their lungs are really little. When they're little and only 4 or 5 pounds, their lungs are small. But two, when they inhale, they take their first breath, just like we were talking about with Boyle's law, right? They increase the volume decreases the pressure, sucks air in. That opens up those airways, but inside of the airways is moisture. So the inside of the lungs is very humid and moist. Water likes to cling together. So if they don't have what's called surfactant, when they exhale, their lungs will actually completely collapse. So the water inside of the lungs will pull the airways closed. So that means the next time they breathe, it takes an awful lot of effort to pull the airways open. And so literally, like every time they take a breath, it's like they're taking their first breath because the airways close down. That is because you naturally make a chemical in your lungs called surfactant. And surfactant is kind of like soap. So it helps to decrease the water's clinginess. It helps to decrease water's desire to like stick together. It helps to keep those airways from closing down. So it's interesting, people that have a preemie, they'll put the baby on steroids because that'll help to speed up the development of the lungs. But they actually have an artificial surfactant, and it comes in a can that looks like WD-40, right? So what is WD-40 is the blue can, and always on it is a little red straw. So baby, typically, if they're having respiratory distress, they may have to ventilate them, which means that they put a tube down and they're helping them breathe. But they can take this surfactant, stick it down in the airway, and like couple of squirts, and that's like soap that coats this lining, and that helps to reduce the surface tension, reduce the clinginess of water so that they can actually keep their airway open better. So then they do that every once in a while as they're needing it. And then as their lungs grow in complete development, they'll start making their own surfactant. But that was one that they discovered. They didn't know before. So 20 years ago, if you had a preemie earlier than 35 weeks, they didn't have very good outcomes. And it's because they would get in respiratory distress, and those respiratory muscles would get so fatigued they could not breathe. Like the muscles would quit. So now babies that are like 30 weeks have a really good chance. They call them little micro preemies. Like when they're the pound and a half babies, they look like little birds. They're really tiny, but they can come through and end up being normal and functional. They're a little behind size-wise and everything else, but they can catch up and have no ill effects. And it's because they can use things like this to try and make sure that they're getting good oxygenation and kind of like helping their lungs inflate the way they're supposed to without so much muscle fatigue. So that's cohesiveness. Last one. Water, they call it the universal solvent. And that is because water is polar in hydrogen bonds, so it likes to interact with anything that's polar. So any polar molecules like sugars, remember all those alcohols on the sugars, those can interact with water. Water also interacts with salts because water has that slight charged nature, and it's going to be attracted to the charged nature of salts. So any kind of salt you eat, any kind of polar molecule that you eat, mixes with your saliva and can get absorbed directly into the blood. This runs into the problem, the problem of lipids, right? So in our talks, lipids are nonpolar. So lipids do not stay mixed. So we're going to talk a little bit about what you have to do with lipids in order to get them to stay mixed and dissolved, even though they're traveling around in this polar blood. Okay, so I'm going to quit there. We still have the salts. So in the five intermolecular forces, we have the non-polar London forces. Then we have the polar dipole, the fancy polar ones, which are hydrogen bonders. And then the last two are the salts. How salts interact with polar molecules, and then also how salts interact with each other. Okay, so we'll go through those next time. And I'll do, I just threw it. And I'll do like, sort of like looking at molecules to describe or determine what kind of intermolecular force would you see in a group of these molecules. We'll talk about those ones next time. And then that leads us into, we're not going to talk about any of that. Talked about solubility. We're going to talk about soap. We made soap in lab, so we're going to talk about soap. And then the last thing that we're going to talk about is cell membranes. So I think we should be able to finish all of those next time because membranes are a good example of polar and non-polar, how things end up forming layers, but that'll finish up chapter 7. Chapter 7, the gas laws is the math, but other than that, it's just kind of theory. And a lot of this stuff we've actually talked about, polar and nonpolar and how covalent molecules do that. So we've talked about those otherwise.
And the math is just